Let's do an example of kNN, of k nearest neighbors. As an example, we look at a paper that studies 779 chemicals and whether they're stored in the body. If they are stored in the body, we indicate that with the response variable stored being equal to 1. If they're not stored in the body, if they're eliminated or metabolized, then we indicate that with stored equals 0. Stored is our response variable. 9 molecular measurements on each chemical are used as predictor variables. We load the data from the bioconcentration.csv file, and this data comes from 2 papers, and it was downloaded from the UCI machine learning repository. Here's what the data look like. You see the 9 predictors as the first 9 columns, and then stored either being 1 if the chemical was stored in the body, or 0 if it was not stored in the body. First, we do some data cleaning. This is often the hardest and most labor-intensive part of data analysis. I've heard experienced data analysts say that they spend 90% of their time cleaning data. We replace each of the predictor variables with their measurements in standard units to put each variable on an equal footing when computing distances. Then we shuffle the rows to avoid bias in the order that the chemicals were listed. For example, we don't want the toxins to all be listed first. And then we finally split the data so that about 60% of the rows, 469 rows, appear in the training set, and 20%, 155 rows, appear in each of the development and testing sets. I've also used the np random seed command here so that when we do our shuffling, you get exactly the same results. We replace each predictor using this code here, and we're replacing with each predictor with its corresponding value in its standard units. And then we shuffle the rows. Notice we're using with replacement equals false in order to shuffle. And then we take various proportions of the data in order to make the train, dev for development, and testing data sets. 9-dimensional data is hard to visualize, but we can plot 2 of the dimensions. The plot below makes it look pretty unlikely that we'll be able to distinguish the chemicals that are stored in the body, the blue dots, from those that aren't stored, the red dots. And I don't expect you to be able to produce plots like this, but the code is provided here in case you're curious or need it for a follow-on class. Now, we provide a collection of functions that allow us to implement k-nearest neighbors. Again, we don't expect you to program such functions on your own, but you may want to follow the thinking behind how we implement k-nearest neighbors. We start with some distance formulas. The distance function finds the distance between 2 points in 9-dimensional space using an extension of Pythagoras' formula. The function all distances finds the distance from each row in a table to a given point. And the function table with distances takes a table and returns a larger table with an extra column containing the distances from the rows to a point. The function closest finds a table containing the k closest rows in a table to a point, and the function majority returns the class, either 0 or 1, of the majority of the rows in the table produced by closest. Then the function classified point finds the k-nearest neighbor prediction for a given point, and the function classified dataset computes an array of the classifications of the rows in a table. Let's find out how we did. The function accuracy takes as input 2 tables, training and test, each containing the response variable as the last column. We also provide a value for k, the value in k-nearest neighbors. The function returns the accuracy of our predictions. That is, it returns the proportion of the rows in the test table that were correctly classified. Here's the function accuracy. And let's try to apply the accuracy function, training the 3 nearest neighbor model and assessing it on the train data, which is not what we ought to do in general. You shouldn't assess your model on the same data set that you're training, but what the heck. 84%. 84% accuracy is very promising. That's pretty good. Probably too good. We really ought to assess whether this kind of performance persists on another set of new data, like the development set. Let's try that. Let's train on the training set, assess on the development set using k equals 3. 70% accuracy. Still decent, but that result should temper your initial exuberance, yeah? Still, we could have done better by choosing, could we have done better by choosing a different value for k? Maybe. We could try a bunch of k's. We could try k equals 3, 5, 7, 9, 11, 13. We try a bunch. It's helpful to use odd numbers because then we don't have ties for the majority vote. So here I make an array of k values, and then we'll just compute a table that happens to have the accuracies in it. Okay, here's our accuracy scores, and you see that the accuracy goes up when we go from k equals 3 to k equals 5, but then it starts decreasing again. So this data tells us that we should use k equals 5. And we should use a completely different set to assess our k equals 5 model. We'll use the test set to assess the model. We'll train on the training set, we'll assess on the test set, and we'll use k equals 5. Our model achieves close to 71% accuracy. That isn't bad, but there's a simple algorithm that gets almost 65% of the answers right on the test set. And that's a very simple algorithm. We just predict that every chemical is stored. Every chemical has class 1. Indeed, nearly 2/3 of the chemicals are stored in the body. The two classes, 0 and 1, are not balanced. This is an example of the class imbalance problem. When the classes are not balanced, you may want to optimize a different quantity rather than accuracy. For instance, we may want to minimize the number of chemicals that are stored in the body that have stored value 1, but that are identified as not being stored in the body, that have predictive value equals 0. These are called false negatives because we predict a negative, we predict that stored is equal to 0, but the answer is really positive. So they're false negative predictions. Let's write a function, false negative rate, that computes the false negative rate. That's this function here. And then let's calculate the false negative rate for a variety of different k's. Notice that when we calculate the false negative rate, we're calculating on the development data. And we'd like a low false negative rate. And the false negative rate starts out somewhat high when k is 3, drops for a little bit, and then starts increasing again. And in this case, again, it seems that k equals 5 gives the best model. And we could determine what the false negative rate is on brand new data by assessing, by first fitting on the training data, and then assessing on the test data with k equals 5. 36%, even better. We get less than 40% false negatives. There are many other quantities that you might want to optimize, and I've given a link here to a Wikipedia page that has formulas for all of them. But one word of warning, try to pick just one quantity to optimize. trying to achieve good results in several areas at once can cause problems. It's the problem of the horses pulling in different directions. Yeah, if you've got a team and everybody's trying to optimize different quantities, you're going to run into issues. Let's pause just for a moment and answer the question, what to do next? One good thing you could do is to look at the errors that we made. We could, we've done this already when we analyzed residuals for linear regression. And here we might want to look at the chemicals that were misclassified, or perhaps just the false positives or the false negatives. Is there some common pattern there? By focusing on our errors, we can sometimes see a way to make progress. There's much, much more to machine learning and data science. If you're interested, you could contact faculty in the math or computer science departments to learn about additional courses in these areas.